Hi everyone, welcome back to chapter 1.1 reactions rate. So in this video, we are going to talk about order of reaction. So order of reactions can be determined using three of the following methods. The first one is the initial rate methods. So for this method is by comparing different sets of experimental data to get the order, and then only we will be able to get the rate law. Secondly, the half-line graph method. So for this half-line graph method, we need to plot the graph of concentrations against time and look at the trend of the half-life. Lastly, the linear graph method. So for this linear graph method, we need to plot the graph based on integrated rate equations for zero order, first order, and second order to see which graph will give you a straight line. So first of all, methods. So we want to comparing the rate law between two or more sets of experiments. So let's look at the example questions 1. L reacts with M in a reaction and the data is recorded as shown below. So in this data over here, you can see we have experiment 1, 2, 3, 4. We have the concentrations for L, concentrations of M, the initial rate of reactions. So the units given over here is mole per liter per seconds. Based on these questions, we need to determine the rate law of the reaction. Take notes that before you find the rate law, okay, you need to identify what is the order of reactions for L and also for M. All right, so first of all, from our experiment data, you need to choose two sets of experiment to do comparison so that we can solve one of the unknown for either the reactant L or M. So first of all, let us do some unknown. We put the rate law as an unknown with an unknown K, with an unknown M, and unknown N. So remember that for this M and N, the power or the order, you can use different letters. So for example, if I don't want to use M or N, I can use X and Y, A and B, and etc. So first we choose experiment 1 and 2 to do comparison. Okay, the reason why we choose experiment 1 and 2, if you look at the concentrations L, they are different, but for concentration M, they are the same. So when you have the same concentrations, that means we can cancel off. So leave with only one unknown for this L. So we can solve it one at one time. Okay, so experiment 2 on the top, experiment on the experiment 1 at the bottom. Doesn't matter lah, you can swap it over. You will still get the same answer. So the same rate constant we can cancel off. Okay, and then over here you have this N with respect to the concentration M, they are the same, so we can cancel off. So you will eventually get the unknown M with value 2. So this value 2 refers to a second order. So in your sentence, the order of reaction with respect to L is second order. Please have a corrections in your notes. Okay, if we write in sentence, so we are not accepting the number 2, but you have to write in the second order. Alright, so next one, we want to compare another two cells. So for experiment 3 and 4, if you can see over here, concentrations for L are the same. So we can cancel off and leave with only the unknown N. Okay, so K and K cancel. Concentrations for L cancel as they are the same. Then you leave with N. So now you get the value 1 for N, and this one refer to the first order. So write down your sentence. The order of reactions with respect to N is first. Alright, so now once you got the order of reaction for L is second and for M is first, then we can write our rate law. Rate equals to K, concentrations L raised to power 2, and then concentrations M raised to power 1. So you can see that the overall order of reaction is third order. Okay, 2 plus 1 give you 3, third order overall. Calculate the rate constant K. So you can substitute the data from experiment 1 into the rate law. So this experiment is randomly. You can choose experiment 2, 3, 4. It doesn't matter. Okay, so rate equals to K, the rate law just now we found it, and then we just do substitution using data for experiment 1. So you find the rate constant equals to 5 times 10 to the power of 5 L square per mole square per second. So this you need it on your own. So just now we say the overall order is third order. Okay, overall order is third order. So according to this rate law, rate we have the unit mole per second. We can use it mole per second first to derive it. It will be a little bit simpler. Equals to K and then concentration L raised to power 2. So we have M squared. And then for concentration M raised to power 1. So to derive the unit of K, M as -1 divided by M raised to power 3. So now it lives with M to the power of -2 per second. But since the questions give you mole per liter first, so you see, you look at the data given, all is in mole per liter. So if you want to convert, you just do substitution. Mole per liter equals to capital letter M. Okay, and then here you go. It gave you mole -2 L squared and then S -2. You just slightly do some rearrangement. Yeah. But anyway, if you want to keep it like this, mole -2 L squared per second, that's okay. That's fine. So both of these are okay. Alright, so for second example questions, the oxidations of an aqueous solutions of iron 2 to iron 3 in an acidic medium is shown below. So given in the equations over here, you can see we have three reactants. So the table below shows the data for the rate of reactions at 298 Kelvin. So please label down this one as experiment set 1, 2, 3, 4. So we have reactions rate, okay, and then we have concentrations for Fe2 plus, H plus, and nitric ion. Okay, so first questions, determine the order of reaction with respect to each reactant. Write the rate law for the reactions, and lastly, to calculate the rate constant K. So first of all, let's just do our unknown. So let's the rate equals to K, concentrations of Fe2 plus raised to power X. If you want to put it M and L, also can. So in this case, madam put it as X, Y, Z. So Fe2 plus raised to power X, H plus raised to power Y, and then nitric ion raised to power Z. So in this case, since we have three unknowns X, Y, Z, we need to do it 3 times. So you need to have 3 combinations of experiments to get this unknown X, Y, Z. So first of all, comparing experiment 2 with experiment 1. So in this case, the K we can cancel off. And then for the unknown Y, okay, since the concentrations of H plus are the same, so we can cancel off. And the concentrations of the value for the nitric ion is the same, and we can cancel off. So after solving for this unknown X, you will see X equals to 1, which is the first order for this iron 2 plus. All right, to solve for the second unknown, we compare between experiment 3 and experiment 1. So experiment 3, the set of experiment using the values given over here and then fill in accordingly. So for the rate constant, we can cancel off. For the concentrations of Fe2 plus, we can cancel off since they are the same. And the concentration for nitric ion are the same, so we cancel off. So leave with one unknown Y. So solving this mathematical problem, you get a second order for H plus. And the third one, we're comparing between experiment 4 and experiment 1. So the tips to choose which set of experiment to compare. So if you look at this example, yeah, why am I choosing experiment 4 with experiment 1? Okay, you look at the combination. So you look at Fe2 plus. Okay, 2 of this value are the same, so I can cancel off in my comparison. And then for H plus, okay, 2 of this value are the same, so we can cancel off. So easily, we can solve with the problem or solve the unknown for nitric ion. Okay, so the rate constant, we can cancel off. Fe2 plus cancel off, and then for Y also we cancel off, left with the unknown Z. So solving this, we'll get a second order for the nitrate ion. So after getting all the order of reactions for three reactants, then we can write our rate law. So in this case, this is our part 1 answer. And to write your rate law or the rate equation is your part 2 answer. So rate equals to K concentrations ion raised to power 1, H plus raised to power 2, nitrate ion raised to power 2. So the overall order of reaction is the fifth order. So starting from 0, 1, 2, 3, 4, 5, 6, it can carry on. So depends on the order of reactions for each reactant. Then we sum up everything. So 1 plus 2 plus 2 to give you 5. So fifth order. So for our third question is asking for the rate constant K. Okay, so since we get the rate law, we know about the overall order of reactions, then we can do substitutions. You can choose any of the set experiment here. So I choose set 1. Okay, so fill it accordingly using set 1 data. Okay, and then figure out the value for K. So in this case, since it is a fifth order, we have no idea about the unit for K. So for this unit, you need to derive it separately. Okay, you need to derive it on your own. So again, apply your rate law. So for the rate, the unit is ms negative. I'm using molar per second because it is easier for me to see. Okay, so molar per second, the unit for rate. And then for K constant, concentration Fe2 plus raised to power 1, so that is only 1 m. So concentration H plus raised to power 2, so m squared. Nitrate ion, similar, raised to power 2, so m squared as well. And to substitute back mole per liter, you just simply insert into the bracket, and then it will become little raised to power 4, mole raised to power negative 4, and then second raised to power of negative 1. So which is the final answer in this case. Remember that unit of K is important. You need to put as your final answer. Alright, so the second method to determine the order of reaction is what we call as the half-life graph method. So we need to plot a graph of concentrations of the reactant against times. For these concentrations of reactants according to your questions. So if let's say you have ammonia, then you have to put NH3 in this bracket. So A is general. Okay, you have to fill in according to the questions. Okay, and then we need to identify what is the train of your half-life. Remember previously we talked about zero order, first order, second order. We talked about the train. Half-life increases over time, remain constant, or decrease over time. So that one will guide you into which is your order of reaction. So in this case, if the half-life decreases over time, whereby you have the second half-life smaller than the first half-life, therefore you have a zero order. Okay, this is the overall order, yeah? And if you have half-life remains constant, that means the second half-life is the same as the first half-life, that is the first order, as the half-life is independent on the initial concentration. Okay, and if you have half-life increases over time, the second half-life is more than the first half-life, that is the second order. So recall back the graph we discussed previously. So this is the first one where you have the half-life decreases. Okay, so first half-life is bigger than the second half-life. So when you have the half-life decreases, that is zero order. If you have the same half-life, first half-life, second half-life, all the same, that is your first order reaction. If you have the half-life increases over time, okay, that one will be your second order of reaction. So you need to practice, get ready with your graph paper for this type of questions where you need to plot a graph using graph paper and then according to the skills. Okay, so question number 1. The experiment data for the decompositions of N2O5 gas at 25 degrees Celsius are shown in the table. Plot a graph of concentrations of N2O5 against time. So in the questions already given, which one is your x-axis, which one is your y-axis. So concentrations is your y-axis, the time is your x-axis. So from the graph, determine the half-life for the reaction and then calculate the rate constant for the reaction. Alright, so if you have downloaded your graph, make sure you have your title of the graph. So this is a graph of concentrations N2O5 against time. You need to have your axes. Okay, x-axis and y-axis together with the unit if there is any. So in this case, the y-axis is the concentrations, then we have the unit molar or mole per liter, mole per dmq all accepted. Okay, and then for the y-axis, we have the time and then unit is in second. So make sure you have a smooth curve, but this one method is generated using the computer. But if you're drawing, you need to have a smooth curve. So initial concentration is 0.2 molar. Alright, so for this half-life graph method, you need to label where is your first half-life and second half-life. So here is the tips. So since we know the initial concentration is 0.2, so half of your initial concentration is 0.1. So from this 0.1, you put a dotted line to get the first half-life. So your first half-life is 50 seconds. So label at the bottom over here, you have your first half-life, T half, and then in bracket 1. And then this first half-life is 50 seconds. Okay, you may write over here the first half-life in your graph, 50 seconds. So for our second half-life, this 0.1 becomes our initial concentration. So half of your concentration, 0.1, is equals to 0.05. So we again we put a dotted line to see where is your your second half-life. Okay, so in this case, it stop until this part, which is around 160 seconds. So this one is 50, yeah? Okay, but remember that we start from the initial concentration 0.1 for second half-life. So label at the bottom, starting from 50 until 160. So this is your second half-life. So label it at the bottom. Okay, and then for this second half-life, using 160 minus 50. Now, because we're starting from this point, okay, so it becomes 110 seconds. So we can clearly see that the second half-life is more than half of your first half-life. Okay, or you can also say that the half-life increases with time. Okay, the half-life increases with time. Therefore, this will be a second order of reaction. Okay, this is the second order reactions. Okay, so we double check again. You must contain a title that will give you 1 marks. If both axis and units are correct, so over here will give you 1 marks for axis and unit. If you get a smooth curve, you will get 1 marks for this curve. And then when you label your first and second half-life, okay, with this dotted line, get you 1 marks. And when you label it at the bottom over here, you get 1 marks as well. And for the analysis of data, okay, half-life with the values give you 1 marks. And the descriptions, okay, to describe the trend of your half-life, get you 1 mark. And finally, Okay, to make a conclusion, what is the order of reaction? In this case, second order give you another marks. So in total over here, you have 8 marks, more or less the same. Sometimes it's about 5 to 8 marks like that. All right, so make sure you understand how to plot this half-life graph and practice it again using some other questions given in your exercises. All right, so the third method to identify your order of reactions, we can look into linear graph method. So this linear graph, we need to plot the graph based on the integrated rate equations and rate law. Okay, mainly we'll focus on integrated rate equation. So if you still remember, zero order, first order, second order, we have different integrated rate equation, whereby you need to rearrange to get your y equals to mx plus c. And then you need to determine which one is your y-axis, x-axis, intersect c, and the gradient. Then you need to try and error. Yes, you need to try and error until you get a straight line graph. Linear graph, linear is the same as straight line. So try and error until you get a straight line graph. Then that will be your order of reaction. Okay, since they have different y-axis, so you need to interpret one by one. Okay, so if you look at the diagrams over here, zero order integrated rate law over here, you will get a straight line graph for the graph concentrations against time. So if you plot a graph of long concentrations against time and you get a straight line, that will be your first order. Okay, if you plot 1 over concentrations against time, you get a positive slope, the straight line graph, that will be a second order. There will be only one answer. Okay, there will be only one straight line graph. If you got a zero order with the straight line graph, then first and second order, there might be a curve. So plot until a linear graph is obtained, then determine the overall order of reaction. So for example, if you got a linear graph for the graph ln A against time, then it will be a first order reaction. So let's just try one example. Again, you need to get ready with your graph paper and then try to plot this graph 3 times. 0, first, second, using their own integrated rate law. So questions 1, ethyl iodide decompose at a certain temperature in a gas phase as follows. So you only got one reactant. So from the following data, determine the order of reactions, rate law, and rate constant K. All right, so given here you have your time in minutes. Be careful of the unit for time, and then you have the concentrations. All right, so to plot one graph, the graph of concentrations, C2H5I against time, that will be zero order if you got the straight line graph. And next one you want to plot for first order. So see if you can get a straight line graph. So that will be ln concentrations against time. And then you need to plot the third graph, which refer to second order, which is 1 over concentration against time. Okay, so plot 3 different graphs to see which one you got a straight line graph. Alright, so after you try and error for these 3 graphs, you will see the first graph, which you use the y-axis as the concentrations against time. You will see this is a curve. Okay, this is a curve. So this is not it's not the graph that we want because it's not a straight line. And then the second graph where you use ln concentrations for the y-axis against time, you will see a straight line. So yes, this is what we are looking for. The graph of ln concentrations against time, which show you this is a first order reaction. Alright, so obviously for the third graph, it looked like a curve. So this is also not what we want. You need to do some explanation, and here it goes. A straight line is obtained from the graph. Please mention what is the graph that you are plotting. So ln concentrations against time. Therefore, this is the first order reaction. And then come up with your rate law. So rate equals to K and then the concentration raised to power 1, which represent the first order reaction. And to find your rate constant, you need to find your gradient. Okay, as this one, the gradient equals to negative. How do you get this negative k? Yeah? It's from your integrated rate law for first order. So ln AT equals to negative KT plus ln A naught. So the intercept is actually your N naught, your ln A naught. Okay, so from your graph, your own graph, find the gradient so that you can find your rate constant K. Okay, so the rate constant will be around the range here, 0.017 per minute. Why is it per minute? Because this is a first order reaction and the time given in the table is in minute. Right, so the rate constant will be in per minute. Okay, so for the linear graph method, first marks go for the title, of course, and then the second marks go for your axis. Similar like just now, when you have your correct axis and the unit, okay, both of it correct, you got 1 marks. And then when you have a straight line, make sure in your graph that is a best fit straight line, then you get 1 marks. And then your explanation that straight line is obtained in words, you get 1 marks. What is your order of reaction? 1 marks. Your rate law over here, 1 marks. And finally, your rate constant with the correct unit, which is 1 marks. Right. 1 more marks given for the gradient. And how are you finding the gradient? Also, will get 1 marks. So by using linear graph method, this is the marks that you're going to get. Please try the exercises to enhance your knowledge about these 3 methods: initial rate methods, half-life graph method, and then linear graph method. So there is the end of our chapter 1.1. Please attempt the exercises given.